Good day, everyone. So, our group will be discussing the three fundamental equations of state for real gases, namely the van der Waals equation, Beatty-Bridgman equation, and Benedict-Webb-Rubin equation. Starting off with van der Waals equation, which is one of the earliest developed equations that improved the ideal gas law. So, a bit of background: the equation was developed in 1873 by Johannes Diderik van der Waals, a Dutch physicist who later won the Nobel Prize in 1910. He realized that the ideal gas law doesn't always work, especially at high pressures and low temperatures, since real gases deviate from ideal behavior because molecules actually take up space and they also attract each other. Van der Waals wanted to fix these two problems, so he created a new equation of state. Let's look at the equation derived from the ideal gas equation. So the van der Waals equation is written as the expression shown, where V is the pressure, V is the volume, N is the number of moles, R is the gas constant, and T is temperature. The new terms are A and B, where the constant V corrects for the actual volume of gas molecules, and the constant A corrects for intermolecular attractions. These constants are actually determined from the critical point data of a substance. From these data, mathematically van der Waals derived that the constants A and B are given by the following expression, as shown, where TCR is the critical point of temperature and PCR is the critical point of pressure. Finally, the assumptions and limitations is that the van der Waals equation works much better than the ideal gas law for real gases, especially when pressures are high or temperatures are low. It even explains why gases can condense into liquids. However, it's still an approximation, so it doesn't perfectly describe gases near the critical point or gases with very complex molecular interactions. That is all for the van der Waals equation.
Van der Waals equation is used when ideal gas law fails to predict accurate results, especially at high pressure and low temperatures. In engineering, it has several practical applications. In thermodynamics, it predicts the behavior of real gases. In power plants, it used the steam cycle and turbine efficiency analysis. In refrigerant systems, it helps evaluate refrigerant performance. And in chemical industry, it models gases that deviate from ideal behavior.
Back in 1928, scientists James Beatty and Oscar Bridgman developed Beatty-Bridgman equation to better describe the behavior of real gases. Unlike the ideal gas law, their model worked at moderate to high pressures or to understand how gases act. For the mathematical equation, the Beatty-Bridgman equation is P for pressure, Ru is for universal gas constant, T is for temperature, and V is for molar volume. With this, they added a 5 experimental determined constants, which are A sub 0, B sub 0, A, B, and C. This is to adjust the equation to account for molecular size and attractive forces between gas particles. You can see these gas constants to your property table, which is table 3-4, and their equation became very useful because it gave more accurate results over a wider range of conditions. For the Beatty-Bridgman equation assumptions, this equation works better when the pressure and temperature are in moderate range and gas density is below about 80% of the critical density, while for the limitation, this equation is less accurate when gases are at very high pressures or density and the gas has strong polar forces.
The Beatty-Bridgman equation predicts real gas behavior under moderate conditions and was primarily used before the adoption of more advanced equations of state. In thermodynamics, it can accurately calculate real gas properties below 80% of its critical density, and was often used to model combustion gas behavior in gas turbines and to model the behavior of cryogenic gases. Nowadays, it is primarily used as a benchmark for validating modern equations, and is often taught as a bridge to more complex equations such as Benedict-Webb-Rubin.
Going into our next equation, we have Benedict-Webb-Rubin equation. It is founded by Manson Benedict George B. Webb and Louis C. Rubin, developed in 1940. The purpose of this equation is to create a more accurate equation of state for real gases across a wide range of pressures and temperatures, especially for substances where simpler models like van der Waals or Beatty-Bridgman failed. And also, this equation introduced 8 constants compared to the previous model, which introduced 5 constants. The formula for BWR equation is that P as pressure, T temperature, R as universal gas constants, V bar as molar volume, and the 8 constants shows that it is empirical constants. In breaking down the Benedict-Webb-Rubin equation, we have 5 terms, where first term states that this is the ideal gas parts, where it represents pressure if the gas behaves perfectly, no molecular forces, no volume effects. Second term is that it's all about first correction to account for real gas behavior. It corrects for molecular attraction, pulling molecules together, lowers the pressure, while molecular volume, finite size, increases pressure. Going into our third term is that it adds another correction for high density effects, meaning at higher densities, molecules interact more strongly, so adjustment is needed. Fourth term, it is the very high ordered correction. It is used when the gas extremely compressed near liquid-like states, captures strong repulsion while molecules are almost touching. The fifth term is that it states special correction for near critical and dense regions. It is the exponential term makes the correction fades when not needed. The assumptions of BWR equation works much better than simpler cubic equations for real gases, especially when pressure and temperature cover a wide range, and the gas is nonpolar or a light hydrocarbon. The limitations to Benedict-Webb-Rubin equation becomes less accurate or less useful when the fluid is polar and empirical constants are unavailable, or when higher accuracy multi-parameter EOS are required.
Now, let's head on for the BWR equations. Is one of the most accurate equations of state for predicting real gas behavior, especially under high pressure and high temperature. In engineering, it's widely used in thermodynamics from precise gas property calculations, in power plant to model boilers, steam cycles, and gas turbines, in refrigeration system for refrigerant selection and optimization, and in the chemical and petroleum industries, where accurate modeling of gases is critical. Van der Waals equation is simple and practical but less accurate than the Beetle-Bridgman and BWR equations. Beetle-Bridgman offers the precision in moderate conditions, while BWR is the most accurate and preferred but in high performance and high temperature calculations in industrial application. Engineers choose the appropriate equation depending on the accuracy needed and operating conditions.